Okay, so good afternoon, everyone, and welcome to the 5th episode of the Flexible Power Generation webinar series, organized by ETN Global in cooperation with the ETIPSNet, the European Technology and Innovation Platform Smart Networks for Energy Transition, and 5 Horizon 2020 projects, namely the Flex and Confu, High Flex Power, Pump Heat, sCO2-flex, and Turbo-reflex. I would like to welcome our today's speaker, Ms. Albany Cagnac from EDF, Mr. Fulvio Bellobuono from Baker Hughes, the Professor Paolo Silva from Politecnico of Milan, and Mr. Gaetan Bergin from FIVES. All the speakers today are part of the Horizon 2020 project sCO2-flex, supercritical CO2 cycle for flexible and sustainable support to the electricity system. The project has been funded under the Horizon 2020 call LC 28-2017, highly flexible and efficient fossil fuel power plants, with the aim to develop solutions that would allow the integration of fossil fuel power plants in energy system with a high share of renewables. In fact, in the current energy scenario, centralized power generation is required to increase flexibility in terms of fuels, which translate in being able to burn a wide range of fuels from natural gas to biogas and hydrogen, and in terms of load flexibility. The sCO2-flex addresses the challenges related to load flexibility, enabling centralized power plants to absorb the fluctuation of the grid due to high share of renewables while keeping a high efficiency and minimizing the wear of the power plant's components. The innovative part of the sCO2-flex is the development and the validation of a scalable modular design of a 25 megawatt electric Brayton cycle using supercritical CO2 as a fluid. The turbine in this case is placed in a closed loop and driven by a supercritical carbon dioxide, SCO2, instead of steam. And to do so, the temperature and pressure are always kept above the critical point, which is the point where the phase change between liquid and vapor. The temperature is maintained above the 33 degrees Celsius and the pressure above the 73.8 bar. In this state, the fluid, the supercritical CO2, shows advantageous behavior that are belonging to the liquid phase and vapor phase, such as more efficient turbomachinery, faster load changes, startup and shutdowns, so to enable also higher flexibility of the power plants while reducing the greenhouse emission and also reducing the water consumption. So the project aims at building expertise on supercritical CO2 for electricity generation and its possible application, for example, in the concentrated solar power or in biomass. The challenge here is to develop and validate at simulation level the global cycle, while at relevant environment, the boiler, the heat exchanger, and the turbomachinery. So now, without any further ado, I would like to leave the stage to our first speaker, Ms. Albany Cagnac, sCO2-flex project coordinator and project manager at EDF. Albany, could you give us...
Thank you very much, Ugo.
Thanks. The floor is yours.
Share my screen. Okay. So... And just a few seconds. Is it okay?
Yes, we can see.
Okay, thank you very much. So thank you, Ugo, for the very good introduction of the project. So I'm very enjoyed to be here today to present to you the project sCO2-flex, with my partners from Baker Hughes, Fives, and Polyme. And first, I will just give you a large overview of the project. So at the end of my presentation, if you have some questions, feel free to send it or to ask some questions. So as Ugo said to you, sCO2-flex is the acronym for supercritical CO2 cycle for flexible power plant. And our main idea was to develop and validate a very modular design for a 25 megawatt Brayton cycle, which will use a supercritical CO2 as feed. And we think that to use supercritical CO2 will enable to increase the operational flexibility of this type of cycle. So our consortium is very balanced, I think, very good, because we have some very important universities and faculty partners like Duisburg, Stuttgart, Polyme from Italy. We have industrial manufacturer for Baker Hughes for the turbomachinery, FI for the heat exchanger. We have the CVRH and UGV who help us for the boiler question. Also, EDF is a coordinator of the consortium. So as we are not a manufacturer of plant, but operator of plant, we have a huge interest in, it was very interesting for us to bring a lot of manufacturer and university with us in the project. And we have Zabala for all the communication work. So thank you, Gustavo, because I saw you are here today. So what are our main objective in sCO2-flex? The main objective were to increase the flexibility of the current power plant and even the efficiency, especially during the variation of the load and especially during the when you have to operate your plant with during the low load. And as we speak about thermal plant, conventional plant, we cannot forget to try to decrease all the greenhouse emission and to have a good reduction or how to say a statu quo for the cost of the plant, because we know that in our days it's still very difficult to promote some innovation if you are very expensive, especially in fact if you have to operate your plant and you have some renewables, so you have to have a good idea of your cost and to try to decrease as best as possible the greenhouse emission. So now the project is in its third and last year. We will finish in June this year. So we have some very interesting results. During all the project, we develop, we made a huge equipment development. Our manufacturer for heat exchanger, so FIV, with the partner involved in the different work package, developed very interesting new design of heat exchanger. And this heat exchanger are testing now on 2 sCO2 loop in Europe on Stuttgart University and in CVRH in the Czech Republic. Our partner for the turbomachinery, so Baker Hughes, developed some models and a complete design for the turbine, and especially a prototype for the compressor. And this compressor is currently tested on a sCO2 bench test in France in Baker Hughes facilities. The partner involved in the boiler development, so produce a very interesting design of the boiler. We can work in very low charges. It's a boiler for solid fossil, so lignite, coal, and it was interesting for us to try to increase this flexibility because as you know, the current gas plants are huge, flexible, but the fossil, solid fossil plants are not very flexible. So if we can increase this type of plant, it was very interesting for us to see how to operate this cycle. But we don't have only results on the equipment development. We also have results, very interesting results in flexibility. With Polyme, we work in order to make very new strategies in order to operate this plant. And we can say that now we work a lot currently with the engineering division in EDF who operate all our current thermal plant. So we can see that now with this new strategy, with this new type of control, the plant is very easy to control, and we have a density-based control on the main compressor inlet. We can see that the first results for the optimal control strategy shows that we have faster transient. We are working now in order to investigate how faster we are and if these first results could be applicable in the current operation of the plant and during all the lifetime of the plant. And we know that, and it was very interesting for us because we know that a part load down to 20% is equivalent. And it's very interesting because when you have to operate this type of plant, you will have some difficulties because if you have to operate in a very low part load, you will prefer to shut down your plant. And now we show that we can operate during some time as this very low part load, so we can maybe avoid some shutdown of the plant. But this is the first results for the flexibility, for the equipment, and a very important part of the project was to understand and to investigate how this very new cycle will work on environmental sum and for the cost. So during the project, we made some life cycle assessment with the design developed by the partners of the project. And what we show and what we understand is that if we made some comparison with a current church power plant with a solid fossil plant, so coal plant, and we show that we have a very slightly lower but a lower impact on some greenhouse emission with our plant. This is the first graph figures in my presentation. So we have a very interesting gain in the fuel supply because we are more efficient. We have to use less fuel for the same power, the same output power. And we show that the operation of the plant, which is simpler and more flexible, can avoid some greenhouse emission too. And what is interesting is that we try to compare this production with some renewable production. And what we saw is that we can be slightly, we can have same results than current electricity production with wind farm. We are very lower than the electricity production with PV because we use less materials, we will use less, how to say, we will have a reduced footprint. It's very important because we are now investigating the design, the architecture of the plant. I cannot show to you the current architecture because the results are under progress. And we show that we will have a very compact, but more than we expected, compact plant. So what we think is that this type of plant could be very small. So we can put this type of plant for a 25 megawatt or even for the 100 megawatt plant in a very reduced place. So it's very interesting in when you have to produce some power, for example, on island, and you don't have a huge place for your plant. So it could be very interesting. That's what we saw. And we are currently working with the engineering division and Polyme in order to update and to improve all the operation for this plant. And when the current results, which are under investigation, so show a very good impact for the flexibility. The next step will be to, in our project, the next step will be to work in order to understand how we can integrate this type of plant on the market, so with all the different energy production, so as renewable, as conventional, and nuclear, for example. What are the future challenges? I think that in a more large idea for supercritical CO2. So if we want to continue the effort in order to develop the supercritical CO2 energy, I think that we will need a very large scale demonstration, because in sCO2-flex, as we develop a design, but don't build the design for 25 megawatt, we try to make some very industrial choice. For example, with the choice of materials, with some option in turbomachinery, on some option in the heat exchanger. And this option need to be validated now for some cycle which will be higher than 10 or 15 megawatt, because it will help us a lot in order to understand how we can prepare all the industrial sector, so all the manufacturers, for this type of energy. And I think that if we can show that this energy is still very interesting, if we can develop the industrial sector for the many different manufacturers, for heat exchanger, for turbomachinery, we can help to the establishment of a diversified offer. So we will decrease the price of the different equipment of the plant. We need to make some improvement still at the end of the project and after the project for the equipment, because we know that we can find some new cost reduction driver. Okay, it's very important to understand what could be the industrial choice, some hypotheses, some option in our component, in our equipment. We can reduce the cost. We will have more compact turbomachinery, more compact heat exchanger, and more compact boiler. So we can think that we will have less materials used in the plant. But if we need to have very high price materials, we will lose in competitivity. So we have to understand. There is some yields who can be improvements, yes, and we need now, and maybe I think that a large-scale demonstration will be help us to analyze some assumption for all the reliability and the life cycle point of view. Because if we have very compact equipment, maybe we can change our models or paradigm in order to operate this type of plant. And this is the operator who speaks now, because when we discuss with the current operation division in EDF, they are very interesting. They are very curious about how this type of cycle will change their way of thinking and their way to operate the plant. So it's all for me. So I say thank you to you. And if you have some question, it will be okay for me to try to reply, because I think that my partner will help you and will develop some idea on heat exchanger and equipment and flexibility and show you more results of what we made in the project.
Thank you, Albany. Thanks a lot. We have a couple of questions. I will take the first one. Is definitely a clarification question from Peter Jensen. What is the ADP in slide 6?
Okay. So
please try to be short.
Yes, so ADP was, if I remember, the use of very raw materials and the use of natural resources for the building of the plant. So if you remember, in the PV, we will use some very expensive and rare materials in order to develop the different panels, solar panels. In some wind farm, we will use some materials, and what we show is that for the flex plant, even if we have some nickel-based alloy, for example, we have a reduced consumption of materials, so natural resource of the earth in our plant.
Okay, thank you. There is another question, which is, could you please comment on the compressor design control in order to achieve 20% load to cope up the large density variation?
Okay, so I think that for the compressor, you will have more presentation from my partners from Baker Hughes, because I have the reply, but I think that my colleague will be best for me to explain what I understand and what they really do.
Yeah. Okay, so there are some questions, but we have to move on with the next speaker. So I will try to allocate some time at the end of all the presentations. So thanks a lot, Albany. And I would like to move on to the next speaker now, Mr. Fulvio Bellobuono, a senior aerodynamics engineer at Baker Hughes. Baker Hughes is in charge of the design and validation of a new turbomachinery system. Fulvio, could you give us more details on the technology innovation in the sCO2 power cycles?
Okay. Thank you, Ugo, for the introduction. Let me know if you see my screen. Okay.
Yes.
Okay.
Yes, perfect.
Okay. Thank you. Good morning, everybody. Thank you for being here today, and thanks to ETN team for organizing this webinar. I'm here today representing a large team in Baker Hughes, working on the technology innovation in supercritical CO2 power cycles. Today we are going to present the latest development on Horizon 2020-flex project. Ugo just introduced me, so thanks. I can move on. Let's start with an overview on the programs currently ongoing for Baker Hughes. We are on board on supercritical CO2 power cycles project as a partner since 2018, when we have been awarded for a STEP and a FLEX project. Also for this reason, FLEX for us is representing an important technology milestone. Recently, we have been awarded for solar power plants concentrated solar power plants in Spain, and we are under a grant agreement ratification for other 2 projects expected to start third quarter of this year. As just mentioned by Albany in the previous session, the cycle selected for H2020 is a Brayton cycle with recompressing layouts and flow split. So we have from the turbomachinery side, 2 compressors, the main one and the bypass one, plus an expander turbine. Both compressors operate between 80 and 250 bar, but the main one in particular is operating very close to critical point, where thermodynamic quantities are characterized by large gradients. For this reason, the Baker Hughes deliverable is to design the turbomachinery for a pilot plant of 25 megawatts. But we have also the commitment to design and test a compressor, a prototype, working exactly in these conditions. For all the system, it must be guaranteed the scalability for a power plant up to 100 megawatt. Let's focus now on the technology challenges and the related features adopted on the turbomachinery, starting from compression side. Here we can see the prototype we have designed and machined in our facilities, equipped with the special instrumentation inside to monitor compressor behavior during test. It is a barrel-type compressor with 2 stages, bearing span just above 1 meter, running at rotating speed around 11,000 for a pressure ratio 3. So it is a high power density machine. Power density is the ratio, is the power to inertia ratio. And this is a benefit coming from using supercritical CO2 as working fluid. A clear advantage in terms of plant footprint, cost, and overall cycle efficiency. But on the other hand, we have to consider that we need, for these special applications, a partial redesign of some machine components. For example, the impeller, the first impeller main compressor, has been redesigned in collaboration with the Politecnico di Milano in order to mitigate the sonic blockage effect triggered by the reduction of saturation margin available at impeller intake. For bypass compressor, as it is working far away from critical point, this redesign has not been necessary. The drag seal system also has been revised in order to manage the possible phase change during operation. In particular, the primary vent circuit has been enlarged and pressure safety valves added in order to avoid clogging due to sublimation that can be met during one of the failure scenario considered. Another important aspect is the teardown requirements, very crucial for the plant flexibility. This has been met using variable inlet guide vanes and frequency driver electric motor on both compressors. Let's move now on the expansion side. That as for the compression side, benefits from using supercritical CO2 as working fluid, leading to a compact machine design if compared with the standard Rankine cycle steam turbine. But if we consider that in this situation, the supercritical CO2 is characterized by a high heat transfer coefficient, the thermal stresses can be critical and must be carefully considered. For this reason, and considering a possible full load rejection that can happen during the entire turbine lifetime, the design choice has been addressed to use nickel-based alloys for rotor and inner casing instead of standard martensitic steel that has been instead kept for the external casing and valve body. Also for the expander, the sealing system is a point. In fact, the drag seal system is the most effective technology to minimize leakages. But it is well known that the operating temperatures should not exceed 250 degrees. For this reason, a dedicated cooling system has been designed in order to cool down the hot gas in contact with the system. The machine is an extreme power density machine, and this is a benefit coming from using the supercritical CO2 as working fluid. But in general, we have to emphasize the concept that small machine does not mean design simplification. In general, this is not true, but in particular for this kind of applications. Let's have a look also on the test bench on which we are going to test the prototype. It is a classical closed loop test bench with the bypass circuit and the water cooler in order to control the inlet conditions for the compressor. Also, the test bench is not free of technology challenges. In fact, the inlet conditions for the compressor is a crucial point. It can be demonstrated that 1 degree variation in temperature at compressor inlet may correspond to 30% variation in density and hence in volume. Such variability cannot be considered acceptable for any machine. So the control of inlet density and temperature is a crucial point. As long as also the phase change in transient conditions and the pressurized stop must be considered. And also the piping design and material selection that must be able to withstand the high pressure involved. So as final and general highlights, we have to say that the supercritical CO2 is an opportunity. It's an opportunity to downsizing the machine. From the turbomachinery side is an advantage for plant footprint, cost, and overall for cycle efficiency. But the high power density machines involved requires innovative solutions from different standpoints. Aerodynamics, mechanics, materials, in particular for turbine, controls, and also sealing system. In this regards, we have finalized the design for the prototype. We are now in the commissioning phase. We are ready to start, and in the next weeks, we are going to test this prototype in order to verify predicted performance and to also to analyze, to verify the alignment with the overall project requirements. This is an important technology milestone for all of us. This was the last slide, and I will be glad to answer any question in the Q&A session or now.
Thanks a lot, Fulvio. Yes, we do have some questions. So I'm reading now some in the chat. Can you share information about thermal cycle efficiency, net, and expected specific costs?
Well, honestly, on the thermal cycle efficiency, I can mention maybe with later with Paolo, we will have more information on that. But I can say that with regards to the cycle selected, this cycle is the Brayton cycle with so-called recompression. Okay, so with the flow split, 2 recuperators. Can you see my screen still? Yes.
Yes.
Okay. This cycle is with respect to the simple Brayton cycle with 1 compressor and 1 recuperator is approximately, if I'm not wrong, 10% more efficiency. So the cycle efficiency with this layout may be something around 41, 42%, and it is also stable, quite stable with respect to the flow split between the 2 compressors. There are many layouts, and all the layouts have been considered for the H2020-flex project. But this one, if I remember well, is one of the cycle with a more a stable response with respect to the flexibility, with respect to the flow split between the two compressors, with the efficiency quite stable in the range of 40–43%, while there are other cycles that are characterized by quite lower efficiency for low split ratio and slightly higher efficiency, but only in a tight range of flow split. So but overall, the efficiency of this cycle should be above 40%. Maybe Paolo will confirm, or we will see later. But if I remember well, this should be the overall the number.
Yes, if I can complete just very briefly. So yes, we have an higher efficiency of the current coal plant because the current coal plants are very hard, so they are very low efficiency. We are about more than 40–45%. Okay. And what we want to reach is that to have a very stable efficiency during the part load, because if you have a very low part load, you can have a very low efficiency, and it was not what we want to have in the flex project. So we want to have we have a higher efficiency in a normal part load, 100% part load. We have higher efficiency than the current coal plant. It's okay. We reach maybe we are very the cycle is not optimized as much as possible, but we are very near the current efficiency of the best of best. So the very new plant, so 48%. And what we want to have is to have the very stable efficiency during the part load. It was very interesting, and we made some publications, so there are on the Flex project website, you can see it, and we test more than 41 configuration of cycle, and this configuration was one of the simpler and one of which offer the more stable efficiency during all the variation of the cycle and for the turbomachinery too.
Thank you, Albani. Thank you.
Okay, I can confirm, and I do have some slides on this preliminary result. Mm-hmm.
Yeah, so we are getting there. There was just one clarification question, which I'm not sure this is all clear, because Hughes asked if 1 kilogram of CO2 per kilowatt hour value seems similar to coal plant. Yes, indeed, this is this sCO2-flex.
Yes, this is quite similar, but you compare flex CO2 plant, which is not still optimized by the engineering division. So we are under optimization of all the emission, all the plant, and we will finish for June, and with a very optimized coal plant. So we think that we will improve the results with the sCO2 plant.
Okay, good. And the other questions, I will take it at the end of the session. So let's move on. Thank you, Fulvio, again.
Thank you,
Albani, for clarifying questions. So let's move on to the next, to our third speaker, Professor Paolo Silva from Politecnico di Milano. And Paolo is going to give us insights on the design and development of sCO2 power cycles. So Paolo, the floor is yours.
Thank you, Ugo, and thank you all for inviting me. I start sharing my presentation, so tell me if you can see it.
Yes.
It's okay. Okay, thank you. So I'm from Politecnico di Milano, from the Department of Energy, and we deal in the project with the supercritical CO2 power cycle optimization. The first question we had is, can CO2 be the solution for the fossil fuel power section? It seems to be yes, at least at a theoretical point of view. So CO2 is a safe and economic fluid. It has a very good chemical stability, non-toxicity, non-flammability. It has a potentially high efficiency for the fact we have already mentioned. So for the compression starting near the critical point, we can exploit the so-called real gas effects, leading to a small compression work. Potentially CO2 has very high heat transfer coefficients, much better than any other gas we can use. And this will lead also to compact turbo machines, like already explained. So low pressure ratios, and thanks to high molecular mass, we can have a design of very compact turbo machine with very low inertia. The inertia is also in the terms of thermal inertia because of the compact design of heat exchangers. And so potentially it is interesting. So our aim inside the sCO2-flex project was to make numerical simulation. We made simulation both on the steady state and on the dynamics. On the steady state, firstly, we analyzed the nominal, so the on-design condition, and we tried to optimize the configuration. So we analyzed more than 50 architectures of cycles that are available in the literature. And finally, we selected a couple of them, and finally just one to perform all the simulation. In terms of steady state, we also developed some software, some tools for the off-design simulation. Both the part load, we have to reach the aim of 20% of part load operation with quite good efficiency, like I will show you. And we have to assess the effect of ambient temperature that, of course, will strongly affect a gas cycle in order to assess the annual energy output of the system in a location, for example, in Europe. In terms of part load, we want to optimize the part load operating strategy of the plant, and I will show you something later. The other kind of simulation are about the dynamic simulation. We use Modelica environment to have some programs, firstly to design the control logic, and then to analyze the dynamic response, so the answer to a transient imposed by the operator. This is the most probable. Of course, we have to perform all the calculations, but the selected configuration is this one, is recuperative, recompressed cycle with high temperature recuperator bypass. So we have two compressors, and this bypass is due to the decrease of the stack temperature of the boiler, and contemporarily to have a good coupling in terms of heat capacity at high temperature for the CO2. The constraints are represented here in this table. We have the maximum temperature at 620 degrees, like conventional steam Rankine cycles. 33 degrees is the minimum temperature of the cycle, with a small margin against the critical point, that is 31. The maximum pressure selected is 250 bar, and the minimum one is optimized, and it is about 80 bar. The efficiency of the cycle is 42%, more than 42%. This will lead to an overall plant efficiency greater than 40%. Of course, it is a conservative number. Probably we will result in the end in a higher, even higher efficiency. We demonstrated both the capability to reach 20% part load operation with quite good efficiency, and to answer to very fast transient in order to answer to the increasing demand of flexibility for power plants. We performed an overall simulation of the whole plant, of course, receiving as an input all the data coming from each partner. For example, this is the boiler. We developed a simplified model of the boiler inside our software in order to simulate correctly the overall performance of the plant, both at nominal and part load operation. For example, this is the TQ diagram obtained inside the boiler heat exchanger. About part load operation, I want to say something about this. We analyzed different operating strategies. The first one was to take the minimum pressure constant, the dotted lines, And the second one, that is the best operating strategy, is to change the minimum pressure in order to optimize it during part load, the continuous line. We can see the red curve is the efficiency of the boiler that practically remains constant down to 70% of the load, then goes down quite linearly due to the increase in the air to fuel ratio. What about the cycle? The cycle has a slight increase of the efficiency at part load due to the fact that the heat exchangers are somewhat over-designed at part load, and then the efficiency drops due to the efficiency of the turbomachinery, of course. But as an overall effect, we can say that the plant efficiency is quite stable and quite high. The maximum is at 70% of the load, and then goes down slowly until 50%. Down then 50%, of course, then drops, but at 20% of the load, we can still have more than 34% of overall efficiency. I can say that these are preliminary results published in some papers in literature, but in the end, we could result in an even better efficiency thanks to the design of turbomachinery, especially, that is better than expected. And this is the TS diagram, and the logic at part load simply moves to the right the cycle. So we change the inventory of the fluid. We remove part of the mass of the CO2 from the circuit, putting in a vessel in order to optimize the part load operation. As for the turbomachinery, we demonstrated also the possibility to perform at part load. So this is the behavior of the two compressors, the main one and the secondary compressor at part load. These are the maps, of course, coming from Baker Hughes in a adimensional way, but anyway, you can appreciate that during the operation, we can stay far away from the surge line, so we can stay in a possible working operation with quite good efficiency because we are moving in a high efficiency region. Finally, we wanted to answer to the initial question due to the flexibility of the CO2 potentiality. And so we have to find a compromise between efficiency and flexibility, and to demonstrate that the plant is quite fast to follow the loads. Indeed, if you want to maximize the efficiency, you have to use high efficiency turbo machines, so high number of stages, for example, and heat exchangers with low pressure drops and low temperature differences. That will lead to a quite big turbo machinery and quite big heat exchangers that will lead to an increase in the thermal inertia. So that seems to be in contrast. So the dilemma is between efficiency and flexibility, but it is possible to find a good compromise. We use the simplified approach to have a preliminary design of the overall cycle, overall plant. We took into account the so-called residence time and the metal fluid time constant for heat exchangers. Both of them are expressed in seconds, and they give a feeling, an idea of the inertia of the system and its capability to follow the transients condition. So, for example, the lower is the characteristic time, the higher will be the flexibility, of course. And here we considered a lot of variables of the design of the components. Here is the reference steam Rankine cycle with the same temperature levels. And we can say that looking at this graph, it is possible to design a cycle that is as efficient as a Rankine steam cycle or even higher efficiency, but with a time that is much smaller, so at least 4 or 5 times lower than the corresponding characteristic time of a reference steam cycle. So it seems to be very flexible in terms of dynamics. And indeed, we demonstrated it with Modelica simulations. These are the results. for a ramp load variation from nominal conditions down to 20% of load with a rate of variation of 5% per minute. The dotted lines are referring to the setup variables, and the continuous line is the results of the calculation in dynamic conditions. And you can appreciate that the electrical power output is very well followed. We have some oscillations, of course, of some variables. For example, this is the turbine inlet temperature, but you can appreciate by yourself that the oscillation is within few decimals of degrees. So we can assess that the plant is indeed very flexible. So we can conclude that we have demonstrated the possibility to have a CO2 power cycle applied to fossil fuel that is efficient and flexible, both in the sense that it is capable to reach very low part load operation with quite good efficiency, and also very flexible in terms of dynamic behavior. Okay, so this is our team. I'm the PolyMe coordinator, but I have a lot of very smart guys working with me that I want to thank for their valid support. If you want to contact us, feel free. We recently won another grant from Europe. We are with ETN, you know, probably. We are now finalizing the grant agreement. We are happy to be on board on this team. Okay, if you have questions.
Thanks a lot, Paolo. Very quickly, I would like maybe to take the question from Piero Colonna. So, okay, basically saying that the coal application on which the sCO2-flex is focusing, it seems a little bit outdated given the European trend. Is that aimed at the extra European market, or is there still a market for coal power plants? What is your opinion on this? And then
I don't know if Albany probably is the right person to answer. Yes, we wonder from the beginning.
Yeah, the coal application was a very huge question. Okay, what it seemed important for us was to develop the CO2 cycle for the electricity production part. And when we have to choose what type of application we will do, it was very evident that with the gas plant, we won't use this type of combustion. We maybe use some direct combustion, but not indirect combustion like with a solid fossil. And that's why we have we chose a solid fuel, so coal for the conventional plant. But in the Flex project, we have a study currently with PolyMe too, in order to see what could be the applicability of the cycle without the boiler. So the very simple Brayton cycle with different type of energy. So we are we made some modelization with biomass. And I think that for biomass, we still have a market. We made some modelization for retrofitting with the very hard coal plant. The question was, okay, if we just have to change the electricity cycle, is it okay to use the very hard boiler if we don't want to build a new coal boiler? So we made different assumptions. And I'm okay with you that maybe for Europe, this type of question is very difficult, and as I am from EDF, and we made some discussion and some communications that we won't operate some coal plant, but I think that in the world we have maybe some interest to develop this type of cycle. So maybe without the boiler, maybe with a coal boiler, but just a CO2 cycle as flexible as possible, and to see if it's possible to put it on the very hard plant or in a new type of production, maybe biomass, CSP. We have different projects with different application.
And Albania, I would like maybe to take this question from Stefano Sigali from Enel, because it's really connected. If you can really briefly connect the dots. Can this technology be used as the bottoming cycle of a combined cycle gas turbine? What are the pros and cons compared to the steam cycle?
Okay, we made some studies in internal DF, so it's not in Flex. I won't share it, the results, but I think that now our current CCGT are very efficient and very flexible. And for the game of temperature, for the temperature we have in a CCGT, it will be difficult to change the steam part with the CO2 part. But we can investigate the idea of SCO2 cycle with direct combustion, so like oxy-combustion, so like the alarm cycle, which we use in the net power demonstrator. And maybe we can have some reflection about the use of a bottom SCO2 cycle with very hard combustion turbine, just in order to improve and to add some more small megawatt after the combustion turbine. But the question is very interesting, because we already have made some studies in internal DF, and I think we are not the only one to make this type of studies.
I may add that there is a work package in which we study some extensions to the application. One of them is on the waste heat recovery, also on the exhaust gases of a small size gas turbine, so an industrial gas turbine, and it seems to be promising with respect to Rankine cycle. But of course, dealing with very large combined cycle, it is hard to compare with the steam Rankine cycle. It is still to be demonstrated. It is out of the scope of our study.
Yeah. Okay. Thanks a lot, Paolo and Albani, of course. And now let's move on to our last speaker, Mr. Gaetan Bergin, development manager at FIVS. That they are the company in charge for the development of the heat exchangers. As you have seen from the previous presentation, one of the key components in the supercritical CO2 cycles. Gaetan, could you tell us something more about the challenges related to the development of the heat exchangers? Your microphone is on mute. Yeah.
Okay, sorry about that. So yes, the heat exchanger is a key component of this flexible power generation. And I will present this research about heat exchanger in this particular cycle. So I will explain what was our role in this project. So the maximum temperature and pressure is 500 degrees C and 250 bars with supercritical CO2. And the main objectives, as it was mentioned before, is for the heat exchangers to be as compact as possible, to be also as efficient as possible, and of course with this temperature and pressure to be as robust and flexible as it is required. So for these purposes, we have several steps. So the heat exchanger configuration, and especially the material definition, to have the best corrosion performance. And Then with different partners, for example, with the University of Stuttgart, so some measurements and experiments were performed with 2 different prototypes for collection of heat transfer and pressure drops data, and to have an idea of the limits of the operation of these heat exchangers. And we, in FIFCREO, we have designed the prototypes, manufactured and tested them in several conditions. And another part, as it was presented, was the performance validation and validation by simulation, and especially to have this idea of flexibility. So this was done with these different partners, so with Siverec in Czech Republic and also Polymi in Italy. I will present one type of heat exchanger that was performed, so the plate fin heat exchanger. So the material we used is stainless steel, austenitic stainless steel, for cost reasons, of course. So this technology is principally made of different layers. One layer is made of fins. This is the main component of these heat exchangers. And it is then surrounded by separating plates where we are putting the brazing metal, and we are then have these bars just to seal these different layers. Then you can have an overview of one particular layer. So the fluid is going in through this distributor fins, and then we have the heat transfer specific fins to have the best heat transfer and at a lower pressure drop. So for the manufacturing, you can see that you have the first step is the stacking, and we are brazing under vacuum, in a vacuum furnace in one step, all these different pieces, and we can have a look at the particular dimension. So for the fins, it's about 0.15 to 0.3 millimeters width, and for the parting sheet is 0.45 to 1 millimeter thickness. Then we have the welding of the piping, outside piping, and finally to control that this pressure equipment is validated. For the project, we have this particular to be sure that we have the base material, stainless steel, and a brazing alloy. It's a nickel alloy, and you can see at the end, after the brazing part, we can not even distinguish the difference between the stainless steel and the nickel alloy. So this is between the parting sheet and the bars, and here it's between the parting sheet and the fins. And so we have few intermetallic compounds in the braid joint, so it's less sensitive to corrosion, and it can be compared to other brazing or welded assemblies. We succeed to reach pressure rupture of 1,200 bars. That was not an evidence at the beginning of this project, because we were not able to reach 800 bars at the beginning. So we made substantial work and to be high mechanical resistance, and we're still working on that, especially on fin forming, to go on higher pressure of rupture. So we manufactured during this project 2 types of PFHE prototypes for testing at the University of Stuttgart. So you can see one of these prototypes with serrated fins, and these prototypes mounted in frame and equipped with all these measurement devices. So they perform several measurements in several conditions, and we can see the fanning factor representing the pressure drop versus the Reynolds number, and we are about 20% of the prediction data. It is the same for the Colburn factor representing the heat transfer coefficient versus the Reynolds number. It's quite the same situation. The prediction is really good compared with the modelizations. So with this technology of plate fin heat exchanger, we also designed for the cycle integration for 25 megawatts cycle. And there are two types of heat exchanger. So one named high temperature recuperator. So I present an option with 10 degrees C pinch. The heat duty for the HTR was 90 megawatts in heat duty, and for the low temperature it's about 40 megawatts. So the design, we have an estimated weight of around 100 tons for the HTR, not too far from 50 tons for the LTR. And this was integrated in a cycle simulation model by the partner of people from Polini to perform permanent and transition condition. And we think that this kind of technology permits to have the best cycle efficiency because of the low thermal inertia. And the next point is to test another kind of heat exchanger technology. So this time we don't have plate and fins. We have just a stacking of printed circuit plates. So you can see here, this is a plate of about 1.5 millimeter the width, and then we can have several channels printed on this plate. Here the exploded view of the PCHE prototypes is about 1 meter length, and we are using also the vacuum brazing. Some competitors are not doing the same, but we are using this kind of way to assemble the different elements. And the same at the end, we are welding the pipes and tested this kind of technology. And to finish my presentation, so we have also a view on the microchannels after brazing. So we have a quite good brazing quality between the plates. And after several failures, finally, we succeed to reach not a rupture, because there was no rupture, but 1,000 bars with a rupture with this kind of PCHE. And so we are trying to reach the maximum mechanical strength of these prototypes, and we will test this one until rupture. And at the same time, we have done some other channel shapes plates with, for example, zigzag of 100 angle, and we hope to increase also the heat transfer coefficient with this kind of shape. So I finished my presentation, and so if you have any question about these slides.
Thank you, guys, and thanks a lot. Yes, there are a few questions. One is, have you considered 3D printing of modules and then assembly? If not, what is the reason?
3D printing, yes, of course we perform some 3D printing, but you can see the volume of heat exchanger. So for the 25 megawatts, so it's about 100 tons. We cannot use 3D printing right now to manufacture 100 tons. Actually, it's very small pieces that are done with 3D printing. So of course that could be a good idea, but we don't have the way to do such huge pieces.
Okay, thank you. And next question is, what is the temperature range which is required for the system to work for waste heat to power conversion application?
Sorry, can you precise your question, because I'm not sure what you want to say.
I think this is more like a general questions that we also have discussed a bit before, but this is, what is the temperature range which is required for the system to work for waste heat to power conversion application?
Okay, so in Flex, we optimize the system for a temperature around the 600 degrees. But we know that for waste heat reconversion, we will have maybe a lower temperature. But to be honest, I think that there is a very good solution for waste heat reconversion in different temperatures. So for low temperature, there is a very good solution. So I think that, but it needs to be studying and validate. And that maybe for some waste heat reconversion between 200 or maybe 400 degrees, we can try to investigate if sCO2 cycle could be used for this type of application.
Yes,
and
indeed, I can add something on the waste heat recovery side. We are analyzing a solution coupled to a gas turbine. So the exhaust temperature is in the range of 500 degrees, 550 degrees. So the maximum temperature of the sCO2 cycle is slightly less than 500. And in this case, it is still convenient with different configuration for the cycle, but the simulation are going on. And so 500 can be the reference case for the maximum sCO2 cycles.
Okay, so thanks a lot, Gaetan, and all the other speakers. I think we are out of our time. It's but I believe it was an interesting discussions, and thank you everyone for joining, the speakers as well as the attendees. As written in the chat box, the presentations will be available on the ETN website. I would like also to invite you to register for the next and final episode of the Flexible Power Generation series, in which we will present the Turbo Reflex project. So thanks a lot again to all the speakers and the attendees. I hope you enjoyed the sessions, and see you next time. Have a nice day. Bye.
Thank you.
Thank you.
Thank you all.
Thank you.
Goodbye.
Bye-bye.
Bye.
Bye-bye.
Bye-bye.